Good evening. I'm Alexander Rose. I'm the executive director at the Long Now Foundation. I'm really excited about tonight's talk. I think it was actually Stewart and I were watching the landing live when we both realized we knew Adam Steltzner from a long time ago in Sausalito. So it's so great to have a local person speaking in this series. Couple just announcements. One is that when we do talks here, you probably already noticed that there's bars and you can get a drink and bring it to your seat. So this is kind of a prototype of our salon project that's going to be happening in Fort Mason in a way. And the other thing that you may not have noticed, because I've failed to announce it, is that we do receptions on the mezzanine. And there's more bars, and you can keep talking about all the awesome stuff that you listen to at these talks. So it's a really fun venue in that sense. The other announcement that we have is we just booked our January seminar to bookend the last 10 years of these talks. And if some of you remember that the very first one was by Brian Eno, and he will be speaking again January 21st with Danny Hillis, one of the co-founders of Long Now and the father of the clock project that I work on. So that's exciting, and I think actually this month or next month is our actual 10-year anniversary. So thank you all for coming. And just one more time, show of hands, anyone here see the 2003 Brian Eno talk? Oh, almost 50 people or so, nice. Cool. So as many of you know, we do a long short before these talks. And this particular one was inevitable that we had to do, the 7 Minutes of Terror. I know many of you have probably seen it. There you will see even more of it with some live data mixed in as part of Adam's talk, but there's no better introduction to Adam and the amazingness that happened with the Mars program than this, so enjoy.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels, on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
Good evening. I'm Stewart Brand from the Long Now Foundation. That has to count as one of the best trailers for a movie that hasn't actually happened yet. I have one Mars story. 1976, I was working for Jerry Brown in the sort of the retinue that went around with him. And at that time, the Viking landing, the first landing on Mars, was about to happen. And we trudged down to the Jet Propulsion Laboratory and watched the proceedings. And Carl Sagan was there. And everything, and then we got the first image back that showed the lander's foot on Mars, cheering and carrying on. Carl Sagan was over on a little set next to a model of the lander. And here come the television guys saying, so Carl, do you think there's life on Mars? And Carl says, big smile, there is now. Our next speaker is part of the life on Mars, Adam Steltzner.
This is Mars. For eons, it's captivated our attention. We've looked up at the night sky from before we had an understanding of what was in the night sky, and we've seen something a little bigger, a little redder, a little fuzzier than the rest of the stars in the celestial sphere. We wondered whether it was alive. When we got our early telescopes, we looked up at it, and we saw that it was. It had canals and roadways, landing strips. We saw civilization. Then we got better telescopes. And we realized that those features were, in fact, just natural features on the surface of Mars. But we never shook the thought that maybe Mars was alive. And that's maybe understandable, because are we really alone in this universe? Are we alone in our solar system? Could our nearest neighbor harbor life? So about 10 years ago, NASA asked the Jet Propulsion Laboratory to construct a mission to help answer that question. They wanted us to put a rover on the surface of Mars. And not just anywhere on the surface of Mars, but here. This is the Gale crater on the equator of Mars. It's a massive crater, 90 miles across, about the size of the big island of Hawaii. In the center is a huge mountain, Mount Sharp, standing 15,000 feet above the crater floor, higher than anything in the continental US, in the Rockies, in the Sierras. They ask us to put a rover right down there, sort of between the canonical rock and a hard place, between the crater rim and that massive mountain. This is a pretty cool image. It's actually an image constructed of orbital data taken from the Mars Reconnaissance Orbiter, a science satellite in orbit around Mars. Those are digital images that have been rendered true to elevation and constructed into a digital elevation map. So this is actually what that crater would look like if you were able to fly an aircraft at about 60 or 70,000 feet above the surface. That image used to keep me up at night. It used to make me feel sick to my stomach because of the challenge of getting down there safely. If you're going to Mars, you have to do 4 things. If you're taking anything bigger than a bread box or smaller than a house, you have to do these 4 things. In orders of magnitude, you hit the atmosphere going about 10,000 miles an hour or so. If you're coming from Earth, heading to Mars, that's how fast you'll be. 15, 10, we did 13,326 miles an hour when we slammed into the atmosphere. That's fast enough that there's enough kinetic energy, enough energy of motion to vaporize the entire spacecraft. Can't let that happen, so we wrap the spacecraft in a special shell, an aero shell, and it's a carbon fiber structure, generic aerospace structure, but coated with a very special material that resists the heat, that smolders but does not burn, and allows us to reject that kinetic energy to the atmosphere. Essentially, we burn a hole in the sky on Mars when we hit that atmosphere. That slows us down a lot. It slows us down to about 1,000 miles an hour or so. The specifics for Curiosity are about 800 miles an hour. Not slow enough, open up a parachute. As Anita, one of my teammates, mentioned in that video, it's the world's largest supersonic parachute. That takes us down to a couple hundred miles an hour. As Tom mentioned, that's certainly not slow enough to land on the surface of Mars, and so we go to rockets. Now, in general, that set of things has to happen because Mars doesn't have enough atmosphere to handle the parachute that will slow you down all the way to the surface. And so you're left with going to propulsion. And then depending on how good your prop system is, if it's throttleable or not, if you've got good sensors that are sensing the ground, you need to deploy or employ a final touchdown system. Something to take out the last 1 to 10 miles an hour, that last sort of gentle embrace, the kiss with the Martian surface. There's the old vaudeville joke, right? It's not the fall that kills you, it's the landing. Even though the kinetic energy of that final touchdown for MSL, for Curiosity, the rover, was less than 0.03% of the arrival kinetic energy. It was, in some sense, that which we struggled with most. But just to get down and fit between the rock and the hard place, we were going to have to innovate starting at the top. Because if you, here's another image of the Gale crater. This is shaded relief. Orange is high, blue is low. You can see Mount Sharp in the center and the crater rim on the outside. What we've done is we've overlaid on that the landing ellipses, the uncertainty footprints, we call them ellipses because they're ellipsoidal, of all of the successful US missions to the surface of Mars, which essentially are all the successful missions to the surface of Mars. And there are unsuccessful Russian missions and there are unsuccessful US missions. But the ones that made it look like that. And you can see over time, starting with Viking and moving forward, we've done better. Some of that was based on our ability to navigate between the planets. So the first reduction is improvements in planetary navigation. And then that occurs, there's a big jump between Mars Pathfinder in 97 and 2004 Spirit and Opportunity, and that's a different, sort of a quantum change in how we do interplanetary navigation using quasars, known fixed locations in the star, in the celestial sphere, radio sources that are well known to better triangulate rather than just our own position and the position of the sun. But that only does so good. And to land down in there on that flat blue spot, we were going to have to do a next quanta. And to do that, we used that guided entry. We took our symmetric entry body and we displaced its center of mass, which meant it flied at sort of a cocked or canted angle. And flying thusly, it developed lift. And we took that lift and we steered it side to side, up and down, to accommodate differences in the atmosphere of Mars, which we never really know about, on the day that we land. So if we show up and the atmosphere is less than we think, we push the lift down and we drag ourselves deeper in the atmosphere and we get more molecules to run into. If there's more molecules than we anticipated, we pull ourselves out of the atmosphere a little bit. And that allowed us to get down there. Unfortunately, when we were going to get down to the bottom there, we weren't going to be landing just any old rover. We're going to be landing the world's biggest rover ever. Here is a family portrait of the rovers that we've put on the surface of Mars. In 97, the Sojourner rover, a tiny little mission. And Mars Pathfinder was the name of the mission. The rover's name was Sojourner. Usually there's a difference between the mission name and the name of the vehicles. Pathfinder is very important because, as Stewart mentioned, we first went to the surface of Mars in 1976. And we went there to try and find life. That's an ambitious question to try and answer in one fell swoop. And we didn't in a way that we could consider conclusive, certainly. And we didn't go back. We didn't go back for 20 years. We didn't go back for 20 years because, well, the price of Viking in, the great thing about the 70s is I can't tell you what the price of Viking is because we didn't keep track. That's called the good old days. Space race, get to the high ground, really Cold War, an active war wrapped in a cloak of civility. So we didn't keep track. But if you go back now and you sort of reconstruct what the costs were, it's probably $5 to $10 billion. And that's a notable investment. We'll wait for later to figure out whether what that means. But in 1990s, the then NASA administrator Dan Golden said, what if we embrace increased risk and look for a strategy to explore at greatly reduced cost? That was the Mars Pathfinder mission. It wasn't pathfinding a way to Mars. We knew how to get to Mars. It was pathfinding a new, lower cost way of getting to Mars. And it did that. It put that little rover on the surface of Mars for $350 million. And no matter what you think we spent on Viking, $350 million is at least an order of magnitude less. Buoyed by that success, we vowed to go back every time we could. It ends up being, due to the celestial mechanics, that's every 26 months. So we did. We had some fits and starts. And then in 2004, we were successful with the Spirit and Opportunity. Twin rovers, 2 rovers on the opposite sides of the planet. Spirit and Opportunity are their names. That's one of them. I can't tell you which one it is because they're twins. But they were very, very important because they showed us that liquid water had been on the surface of Mars. And we know from Earth that where there's life, liquid water is not far from it. And where there is no liquid water to be found at any state, at any time, we don't find life. So that was fantastic. It helped with this key question of, is there life on Mars? But Spirit and Opportunity left some questions unanswered. They couldn't tell us some important things. Was the water salty? Was it sweet? Was it acid, base? In short, was that aqueous environment, that ancient aqueous environment of Mars, was it habitable? Well, in comes Curiosity. She's packed to the brim with all the equipment that you'd need to answer that question. The problem is, she's difficult to land. She's big by rover times, she's big by automobile sizes, human scales, she's large. And we really struggled with how we might land her. Over the course of about 7 years, ending really in 2003, we were struggling with the question of how to land the big rover, which is what we referred to it. And we looked at airbags. We'd use those to land Spirit and Opportunity and a Mars Pathfinder. It ends up being that airbags scale poorly as the mass of the vehicle goes up, and there's no fabrics known to human beings that are strong enough, no fibers that are strong enough that we can make a fabric out of that we could have airbags. We looked at legged landers. Imagine Viking, and you just stick a rover on top. Well, in those fits and starts getting to Mars in 2004, between 97 and 2004, we lost a mission called the Mars Polar Lander, which was a legged lander. And as we went through the failure analysis of that, we reminded ourselves of some of the fragilities or some of the risks associated with those kinds of legged landers. They end up being tippy. They don't tolerate slopey terrains very well. And you put a 1-ton rover on top of it, you have compounded the problem. So they were out. So we looked at trying to solve that problem by spreading out the legs, adding more legs, making a big flat skeeter bug and belly flopping. Unfortunately, the propulsion systems in the belly, it's got toxic and frequently explosive fuel, exploding on touchdown, super poor form. And so we have to armor the belly of the beast. And when we start to armor it, the weight goes up and up and up, and eventually we cannot launch it. So, in the September of 2003, we got everybody together who had ever worked on anything like this, and we went back into a brainstorming session because none of these methods that we had been working on were bearing fruit. We vomited out onto a big table every idea we'd ever had. We cut and pasted, collaged them together, trying to see if we could interpret a new way of doing it that was different or adjacent or better than the ways we'd done it before. Out of that room came something we called at the time direct placement. We rapidly took the name Sky Crane. And we knew two things when we left that room. One, we had a solution that we believed in for very real engineering reasons. And two, we had a solution that would impeach our credibility every time we opened our mouths. In fact, it was my job to open my mouth most frequently. I wonder why that was the case. I may be personally inclined to do so. I developed a little pithy saying that I would start a conversation with in order to try and retain some shred of credibility. That saying goes like this: great works and great folly may be indistinguishable at the outset. It's kind of perfect, right? If it's really revolutionary, if it's really different, it'll look crazy. The problem is that crazy also looks crazy. And so we are left personally in the team, myself, team of about 50 at the core, with the nagging question, are we convincing ourselves of this? Is this really crazy and we're really just all along for the ride? What compounds that is the fact that you can't test this system. You cannot test it here on Earth. The differences in gravity, the differences in the atmosphere, all mean that there's no way we can construct a test vehicle to prove whether we were crazy or not. All we're left with is analysis. First in pens and paper, later ones and zeros, This here is a simulation, one of millions of computer simulations. We've put all the physics we could think of into this model, and we're asking how it works. In fact, right here we're landing the rover on a 35-degree slope that is so slippery that the rover cannot rove, and yet we can land her. So this made us feel very confident. Unfortunately, this kind of analysis only tells you the answers to the things that you ask of it. When, prior to landing, people would ask me, what is the thing you're most worried about? I would answer, very truthfully, the thing I don't know to be worried about. I have a long list of things to be worried about. We go through that long list. We work the bejesus out of every single one of those things until we prove to ourselves that we're satisfied and we accept the risks associated with each one of those. The thing you fear is not the thing you're talking about. It's the thing you're not talking about, the thing you don't know to have on there. And that's not in that computer model. So it all came down to August 5th for us here on the West Coast, Sunday, in 2012, last year, 10:30 at night. And this is how it happened.
Coming up on entry. Vehicle reports entry interface. At this time, it'll begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. The vehicle has just reported via tones that it has started guided entry. Target at this time. We have seen peak deceleration. We should have parachute deploy around Mach 1.7. Parachute is deployed. We are decelerating. Heat shield has separated. We've found the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending. Standing by for batch shell separation. We are in powered flight. We're at an altitude of 1 kilometer descending. Standing by for sky crane. Sky crane is started.
Signal to us, you remain strong.
Touchdown confirmed. We're safe on Mars.
So that was a good night. Infinitely preferable to the alternate fate which awaited us on Mars that evening. I know for myself, and I know that for many of the team, that the numbers that come back that tell you that the vehicle's done its job, that you're safe, all require the front of my noggin to decompose them and figure them out. And that a much more visceral experience that we had accomplished what we set out to is found in these. These are the first images of a new place for us in our solar system. From the left, this is looking at the front of the rover through what's called our hazard cams with the lens covers removed. Nice, clean image of Mount Sharp in the distance. And the, I meant to the right, your left, my right. And black sand dunes between Mount Sharp and us. In the center is the Molly image from one of our science cameras with its dust cover, its clear dust cover still on it, covered in the red oxide-rich dust, giving a very beautifully red-toned view in color for the first time of this new place on Mars. And the leftmost image for you is in fact the very first image of this new place. We had this orbiter that I mentioned, the Mars Reconnaissance orbiter, overflying us as we landed. And we had a data stream, the telemetry, that you saw us reacting to in the control room, all came through that spacecraft. And that link was very important because if we were to wink out or disappear or blow up, we wanted to be able to reconstruct, or hopefully reconstruct, how and why that happened. So we were using that data link. Once we were on the ground, we were losing that link, and we thought we might just have just enough time to get one image. So we chose this image. It's out the rear hazard cams. These are fisheye lenses, low on the rover, that are designed to help it when it roves around. We took that image because we were hoping that we just might see the plume associated with the impact crater when the descent stage flies off to a safe distance and crashes. If you squint, you can see that that is, in fact, what that is. So it was a really good night. Everything worked. On the numbers, we nailed it. That blue, light blue is the ellipse, the green diamond, the red X, and the black cross are variously the spacecraft's belief in where it was, where we thought it would be during the, when we hit the Martian atmosphere, and where it ended up actually being. And they're all right in within a city block. As far as getting to Mars is concerned, that's worth barking about. And after landing, we haven't just sat there. We've moved. We've done other things. All of us landing guys got fired, pink slipped. We got gone off to do other things. But evidently, there's a whole mission that starts when our job is done. And folks have driven the rover and asked questions and gotten some pretty incredible answers. In fact, we are about halfway through the mission, and already we've answered one of the key questions that Curiosity was sent to ask. Was the ancient environment on Mars habitable? Through taking cores, drilling into the surface of Mars and bringing out powdery material and distributing it to a set of science instruments on board, we have an answer. And the answer is yes. If there was life on Mars, or if there is life on Mars, that ancient aqueous waterborne environment would have supported it. It had the right pH, it had the salinity, had the right water activity, I don't even understand what that is, to support life. That's kind of profound. So she's there. She's doing great science. She, as the president's science advisor said, 2,000 pounds of American ingenuity. But I'm left with a question. Why do we do this? You know, why? Is it a particularly practical thing for us to be doing this? It took, it's 10 years, 37 states, 10,000 people, $2.5 billion. It's a good idea? Is it practical? Sometimes I even start to get tripped up as to what is practical. I can tell you some things that I know to be practical. The 737-700 is practical. This is Burbank Airport. I can get via the air stairs onto Burbank. I love that. Just like a bus. It's literally like a bus. And I go down to the Johnson Space Flight Center in Houston fairly often, and that's a trip that I do in 3 hours. When my mother was young, it probably would have taken her 3 days. And when her mother was young, it probably would have taken her 3 weeks. So air travel is convenient, practical. It's had a profound effect on our society. And yet, if you look at the early exploration of what flight's about, it doesn't appear very practical. It doesn't really appear that it had promise of being particularly practical. I can't see the allure. It's more a drive, sort of an impractical, despite the impracticality of it. Early attempts at aviation, the early attempt to explore the heavens was injurious, frequently humiliating, and unfortunately often fatal. But we kept trying, unreasonably. And eventually we succeeded, even though for many years, aviation would still be a very risky proposition. So, it's not practical, necessarily. We can't be guaranteed that it's practical. There may be practical outcomes from it, but we don't do it for that reason. Is it for the science? Science questions. This is an image of Times Square on Monday morning the 6th at 1:30 in the morning. On the East Coast, it was Monday morning at 1:30 in the morning when we landed. Times Square, there's a few thousand people there. I'm told it was a lightning storm. Now, are there a few thousand people sitting on a Monday morning at 1:30 in a lightning storm at Times Square watching the diamond screen because they're dying to know about the pH and salinity of the ancient primordial environment on Mars? I don't think so, or at least not just that. It might be akin to when thousands of people watch an athlete to see if they can run a set distance 1/100th of a second faster than another athlete. When we explore, we're actually asking questions about ourselves as individuals, as a society, as a people. Neil Armstrong actually hinted at it a bit when he chose the words to say when he stepped foot on the moon. One small step for a man, one giant leap for mankind. He was hinting that his act was bringing us with him, that his exploration was our exploration, that our society, our us, was somehow being, to quote Jebediah Springfield from The Simpsons, embiggened. So exploration asks questions like, who are we? How grand are we? What is our reach? What questions might we dare ask and believe we could hope to get the answer? So I don't think exploration is practical, but I do think it is essential. I think it is an expression of our humanity. In the same way that we sing. I'm not totally sure of the utility of singing, except that it makes me very, very happy. Art, architecture. There are all sorts of beautiful things. Almost all of the beautiful things that we humans do are considerably abstracted from their obvious need. That's one of the great things that makes us us. So, we've got great things in the nowadays in front of us. So Mars sample return. It ends up being that all the ingenuity you can pack into a 1-ton rover does not match the ingenuity sitting in this room, certainly sitting on this planet. And so to really answer the question about whether Mars was alive or not, we may well have to bring a piece of it home. And I'm actually working on what might be involved in doing that. Europa, the icy moon of Jupiter's. I'm not an exobiologist, but I drink beer with exobiologists. It makes me feel like an exobiologist sometimes. And they tell me that one of the key places, one of the, number one spot in our solar system that could have existing life today is Europa. I certainly hope in this next few decades we put a lander on the surface to see what life may have upwelled in that ice and be present on the outside surface. Titan, the moon of Saturn. We know that there are methane lakes, a rich organic compound. Methane lakes the size of Lake Superior on the surface of Titan. What else are in those compounds? How important might they have been in early formulation of life? These are questions that we have in front of us. These are things we do with robots. These are things that I do with robots. But if this is such an essential human thing, if this is an essential expression of our humanity, it makes sense that humans also would be physically involved. And I think they will be. This is an image of a possible Mars transfer vehicle to take humans to the surface of Mars. It's much harder to take humans than it is to take a robot. we designed Curiosity to withstand 15 Gs on entry, and that 15 G pulse lasted about 16 seconds or so. That would kill a human being. In fact, humans we've known since the 50s are kind of delicate. Consumptive, cranky. They need water and food. They don't tolerate radiation very much, and there's a lot of radiation in the universe. Outside of the magnetic field in this planet that shelters us from the streaming radiation from the sun, it's a very nasty place. It's unconceivably cold or indescribably hot, bathed in radiation. It's unfriendly. And keeping humans alive and happy in that environment is a challenge. But I think we will do that. And I think we'll see that happen in the few decades from now. It's hard to predict. With the way we do business today, it's quite expensive. And those expenses might be hard to choose to accept. Right? If it were $50 billion, people sometimes say, when are we going to have humans on Mars? I say, well, you know, when you start to see a $10 or $20 billion a year surplus in the federal budget, it could happen any time. What about colonization? What about going a step further? There are folks who propose colonizing the planets. Certainly Mars is a very popular one, and we could imagine colonizing it in the near future, decades, using current technology. This is an example of an image from Mars 1, folks, about what that kind of colony might look like. Personally, I'm not sure that that's a colony. That looks more like an outpost. There are places on Earth that we have explored, but that we have not chosen to really live. An example might be Antarctica. This is actually another outpost. It looks a lot like the previous image, but this is the Halley 6 station for the British Antarctic expedition on an ice shelf. And there are 14 people who live there year-round, and it blooms up to, let's say, 50 or so. But that's not really civilization. And it's supported a lot by material and people from the places that are not like this, right? Like the places that are like this. But, so if we really imagine colonizing space, stretching out from this Earth, outside, we're going to need to go to places where we can really live, not that we can just eke out a subsistence. And that means things like terraforming or world ships. This is an artist's rendition of a possible terraformed Mars. And this is a world ship, a ship that could be moving or could be stationary, but would have all of the attributes of our planet in it, or many of them, the important ones. A lot of people I talk to are attracted to this as a cure for what ails this world. Because we're going to be overpopulated, or because we're going to pollute this planet, or because we're not going to be able to get our shit together. I think that that is a cop-out. I think that is short thinking. Because there are no skills necessary in accomplishing either of these two goals that are not those same skills required to maintain balance and equilibrium here on Earth. So, I have lived in many houses in my life. Some of them have been large, and some of them have been small. But all of them have been equally cluttered and messy. The problem is not the size of my house. So when I think about space exploration, when I think about what it means in the long, the best thinking that I can do brings me back here. That we learn, like we do when we travel this earth away from our homes, new and beautiful things that challenge our minds, that expand our understanding. But when we return home, we see it in a new way, in a better way, in a deeper way. I think that's what exploration does for us. I think it is fundamentally human. I think it is essential. But I don't think it will solve the ills of this planet. I think that is for us to do here at home. Thank you for your attention.
Have a seat. Liam asks, that self-portrait of curiosity was done how?
I was hoping nobody would notice. We actually have 5 vehicles on the surface of Mars, a few camera vehicles that take different images. Actually, so those are composites of many, many images. We use it's using a science instrument actually, the MALI, the Mars Hand Lens Imager, on the end of the robotic arm. It's made to have a very wide focal length and be able to focus very close up, looking at microstructure of rocks, and also to be able to get views up to a few meters away. And so we take images, many images, hundreds of images, and we make a mosaic. And so we can choose, if we want to take the images that eventually erase the arm. And that's what we do. It's the easiest because the arm shows up differently in each of those images, very much differently in each of those images because it's close to the imager and it's very difficult to rectify all of that. So we choose it so that they're gone. So it looks like the camera vehicle is taking the image.
It would be fun to reproduce that right here. You have this camera and then, anyway. Rob Carlson asks, the surface of Mars is like Clorox mixed with sand. Earth bacteria are found thousands of feet deep in ice and mud. How deep do we drill to find any surviving bacteria on Mars?
That's a good question. One of the fun things about me is I'm willing to speculate on things that I'm absolutely unqualified to answer. So let me do that now. My understanding from really just sitting around in rooms with people who understand this stuff and listening to them speak and having them ask me to do stuff is that there's certainly what is called a weathering rind, about 5 centimeters that is most eroded by radiation from the sun and oxidation from the atmosphere.
What's the radiation like on the surface of Mars?
It is substantially higher than the radiation on Earth. Mm-hmm. I don't have it off the top of my head, but the exposure is several orders of magnitude greater than, I showed a bar chart of it.
Not something we'd want to walk around in a spacesuit?
Well, you could walk around in a spacesuit if, based on what we know today, if you were to take humans and not take countermeasures, mm-hmm. and you were to take them and do the quickest trip to Mars and back, you'd give them over an order of magnitude higher radiation dose than the Department of Energy allows any of its workers to see annually.
Right.
So it may well have an observable effect on their health. Now you would take countermeasures. You put them in water-lined. You use water as insulation for the radiation. And so you can do a lot of things to knock that down. But it's not a place you can walk around unshielded. So to answer the question, I know that when you get 5 centimeters below the surface, you're into stuff that is thought to be free from that constant weathering bombardment, and is the things that the scientists are interested in looking at back here on Earth for signs of biological activity. So in that sense, they think they can get to some of it at least within about 5 centimeters of the surface.
A lot of people here probably saw the movie everybody's seeing now, some at the IMAX theater, Gravity.
Yes.
Have you seen Gravity?
Unfortunately, I have, well, not unfortunately. Fortunately. Fortunately, I have a.
She lives. Oh, that's right.
Well, now I won't see it. I have a young daughter, 14-month-old, so I have not seen a movie in 14 months.
Well, nor will for another 2 years, right? Nevertheless, Gravity's out there. It's blowing people's minds.
Right.
They get a more
The trailer
of a sense of
makes
reality.
me so freaked out, it's not even funny. There's something so primordially alone about spinning off into space. Yeah, so, yes.
It's still news to a lot of people that it's quiet in space.
Yeah.
And so one of the shocking effects of the movie is horribly violent things go on.
Silent.
You don't hear squat except
Yeah.
people go, which presumably is what they would do.
Yeah, that's what I
Why
do.
would we send people anywhere in space is an open question, which now that you've had such good luck with robots, it's an open question. Why send people anywhere in space?
Right, so that's a great one. I feel even more qualified to answer that one. So I do, for me at least, personally, I think of what we do as being, I'll get in trouble for saying this, akin to performance art. I mean, it's a sort of an essential expression of ourselves. And so if it is such an expression of humanness, having humans doing it makes sense to me. It's not, not solely. Humans are, tremendously difficult to deal with and expensive to deal with. But you could imagine exploring with human beings as part of it, absolutely, because we're doing it because we're human.
So one of the things that happened that you were describing in the sequence of missions is price goes down, acceptability of risk goes up.
Yep.
And that then raises the question of manned missions, and there's lots of people who seem to be willing to volunteer for a one-way trip to Mars.
Right.
And do you have an opinion on that?
Yeah, I do, and that's, I think, a very, very interesting question. Part of me thinks we might run into like a wall of exploration. I fear it. It goes like this. I argue that most of the people who got in boats and paddled over the horizon drowned. We didn't know about that really because they didn't come back. But life was cheap. I recently read a great book, Death Valley in '49, which is Lewis William Manley's account of his life. And to hear him discuss 7 people dying in a boat with 200 passengers on a day, and being most interested is how they wrap the bodies and slide them off boards into the sea. Not that 7 of 200 people died in a day. Tells you how differently we react today than even just 100 years ago or 200 years ago or 1,000 years ago. Here's the question I have that I wonder. It goes to, let's say, Elon Musk. Elon Musk wants to go to land on Mars. I love that, right? It's it's a little bit like suicide. I mean, which also strangely,
Jumping off a bridge and going up.
Right. But it's a terminal event, right? And our society doesn't accept suicide. We make it illegal. We'll lock you up if you try to do it. So I'm intrigued as to the societal response to what it will mean if somebody says, I'm going to go do this thing, and I acknowledge that the vast likelihood is that I will die, but I'm going to do it because I want to do it, and it's interesting, and maybe it furthers humanity. I hope that we don't reach a point where this is going to sound weird, or I do hope, I could imagine us reaching a point where we value human life so much that we'd have a hard time allowing that to happen. And then what would that mean for us? Is that a good thing or a bad thing? I don't know. So that's my reaction.
You mentioned Elon Musk, and
As an example, there are many people who might have money and want to go do that.
so there's SpaceX doing pretty impressive stuff.
No,
Grasshopper
fantastic
goes up,
stuff.
goes
You
down.
see that 744-meter flight filmed by the quadcopter? I'll go run out and YouTube that because that's awesome.
Do you think the privatization of that aspect of space is a good thing?
I
or
absolutely do. I love the privatization of space. It breaks up the status quo, it agitates, it disrupts, it creates chaos. What comes of that will be better. Whether it will be better exactly in the way that the people who are doing that disruption think it will be, I don't know. It doesn't matter. Right? The system is being agitated and new variants and genetic, right? We're mixing genes, we're finding new suboptimums.
So you're within NASA, yes?
I work at the Jet Propulsion Laboratory, which is a federal, FFRDC, federally funded research and development center. There are lots of those. There are like Sandia National Labs, Lawrence Livermore National Labs. You know, there are DOD and DOE labs. There is a single NASA FFRDC, and that's the Jet Propulsion Laboratory. What that means is I'm a Caltech employee, hireable and fireable at will, but we have a contract with the federal government to do a lot, at least 80% or so, something like that, of NASA work.
Not within NASA, but you're right next to NASA.
Right.
Yeah. And so the privatization is starting to happen. I mean, for a while, we were kind of counting on Russians for a whole lot of
Right.
stuff, and now there's these other players. How does that play out in terms of what you see within JPL and within NASA?
Well, for instance, to stay with Elon's organization, which, by the way, is a fantastic organization, and I think he's a very bright man. You know, the Falcon Heavy may offer the capacity to throw 3 times as much mass at the surface of Mars for a third of the cost. And currently, a launch vehicle ride to Mars is approximately $300 million. It's a little bit of money. It's actually a lot of money. And if that were $100 million and you put 3 times the mass, that may actually be a game changer as to the kinds of things that we try to do, right? The approaches that we take. We might be consumptive with mass and use lower tech tricks because mass is no longer, you know, $100,000 a kilo. It's $1,000 a kilo. So it could well be a game changer.
Andrew Pfister asks, are there any interesting improvements in rover landing strategy for future missions? How would you land a manned vehicle on Mars? How would you land a 3 times heavier thing? The sense I got is this, and it's one of the things that appeared in the profile in New Yorker, is that if, against all apparent odds, the sky crane works, it is a system with a future.
You know, it was funny. I have a friend of mine who was actually the project manager of the mission, who used to joke with me as we were doing the development. He said, "Adam, how does it feel to design the last entry, descent, and landing system ever?" And I don't think. By the way, it felt really freaking cool. But I don't think that. I don't think he's right. There isn't one size fits all. When we look at the sky crane, we see that it actually is relatively scalable, right? The architecture is completely scalable. You could ask if it's scalable at a piece part level, and some of the piece parts, you know, we have a hard time scaling down. Like, for instance, we have 8 engines. They have a certain thrust. They have a certain minimum throttle. If you get too light, you need to go to 4 of those engines, but you can't actually get the dynamic range of throttling that we need out of a single engine. That's why we do pairs of 2 and turn one off. And so you might have to develop new engines to go down. But architecturally, the thing scales all over the place. It's awesome. It does really lots of great things, one of which is it's the first actual closed-loop lander. You know, when a legged lander lands on the surface, it's actually quite hard. The control systems are relatively slow-witted compared to the stiffness of the legs. And all of these systems are thrust vector control. That is to say, if I want to go in this direction, I tilt the vehicle, canting the thrust, and then I go in that direction. So there's a coupling between attitude and translation. Right? And so what happens is you come to land on a slope, and one leg hits first. And quickly, it puts a disturbance in, it puts a moment, a torque on the vehicle, and it moves like this. And so the vehicle starts to go like this. The vehicle says, I don't want to go like that. I want to go straight down. It turns back, gink, gink, again, again, and again. And so you get the skittering that sort of happens. So you can try and control that using more quick sensors that are very, very hair trigger and do a very good job of determining that you've just touched the surface. Interestingly, you know that mission, the Mars Polar Lander that we lost in '99, and that helped us remind ourselves about putting rovers on top of landers. Well, one of, maybe the leading possible cause of the loss of that mission was that those triggers, those foot pads, when we deployed the legs, we came in on rockets with the legs hucked in, and then about 80 meters above the surface, we deployed the legs. Well, that one of those touchdown sensors triggered during the jerk of that deployment, and the vehicle shut its engines off and fell the last 80 meters. Ooh. Does that suck or what? There's other possible causes, of course, but it's challenging. That legged lander thing is challenging because it tends to drive you to take very fast action, very dramatic action at the rise of a sort of transient signal. And one of the things we love about the sky crane is the sky crane's coming down, the rover's underneath, it's on tethers, you can't push on a rope. It comes down, we tell this guy, you will go 3/4 of a meter second down, no matter what. So the rover hits the ground, this guy goes, I gotta keep coming, it keeps going down, and it says, wait a second. My throttle settings are now at half of what they used to be. And we've got little clock springs that pull up the slack, and so we keep going down, keep going. He goes, yeah, sure enough, I checked last second, I checked this second, I'm gonna wait a second. Yeah, they're still at the same level. Well, the only way that can really work is that the rover's no longer being held by me, it's being held by the surface of Mars. So we're not sensing that transient event, we're sensing the post-event state of the vehicle. Right. So if that's a persistent thing, we can take all the time in the world. It depends on how long we may want to make the clock springs. And so we had, we love that. The controller's involved all the way to the surface. You can come in much slower. You can land, what all that really rolls up to meaning is you can land on very uneven terrain, which is great. I imagine when humans go to Mars, they will likely go to places that are not uneven, untreated terrain. I would hope, if I were one of those humans, that I'd be going to a place that robots had been before, and they'd taken a little grader and leveled it out and put some radio beacons, maybe written "Welcome to Mars" in the thing, so that we'd reduce the risk for the human beings. So if that's the case, it may not be that human scale missions also use the sky crane because some of the very necessary or some of the greatest virtues would be wasted on it. And there may be another strategy that's more mass efficient under those circumstances. I don't know. But in the neighborhood of the masses that we're talking about for going to unknown or uncertain terrain, the sky crane really is pretty cool.
Well, thank you. Will it also be then useful for places like Europa and Titan?
Europa, Titan, that's right. That's right. All of those present some slightly different challenges. If you're going to float a boat, or you're going to land on a sheet of ice. I mean, I would love to go to Europa. It looks like, to my eyeball, the way I envision it, imagine you take Manhattan and you knock down all the buildings, but they don't break up. So there's all these like chunky, huge sheets of stiff, slippery stuff at all sorts of weird angles. And then there's a big question for the scientists. Where do you want to land on this? Do you want to land on the side near the top? Do you want to go way, way down into the bottom, into a crack where we have a really hard time talking to anybody else because we're down at the bottom of a well. So, at any rate, whether it would be the key system at Europa, I mean, maybe not. It depends on where we're going in Europa. It depends on what the scientists want. But so, the fun part about this, in 1999, which is a bit ago, I was working at JPL, and I had this epiphany. It goes essentially like this. We have visited and remotely sensed almost all of the objects in the solar system to one degree or another. Now, we might go back to get higher res pictures here and there, do another remote sensing science suite, and there's good reasons to do that. But what we're really entering is the golden age of in situ exploration, where you have to go down and intimately interact with this unknown environment. I'm a mechanical engineer by heart. That means you mechanically interact with this environment. That is work. That is hard. And frequently, it's different at each of the places you might want to go. So it's custom. That is cool. I mean, if you like doing that kind of stuff, which I do, it's a pretty good time to be alive.
You know, I haven't seen you since basically you were a kid in
Yeah,
Sausalito.
it's been a while.
I was
Right.
significantly
I was a
younger.
teenager, probably like 18 or something like that.
Yeah, and you were not someone that I would have said, or would anyone else that we knew would have said, this guy's going to be a major planetary exploring engineer.
Yeah.
What the hell happened?
Yeah. So it ends up being, right? So I don't really know. I'm a little too close to the story to know what the answer to that is.
You've told it a few times, that gives you a bit of an angle.
Yeah, it does. So, I think the backstory, maybe everybody knows it, but I'll just do the quick Cliff Notes version. I didn't do well in school, didn't try very hard in school, to convince myself, and actually everybody else, that I was not going to ever apply myself. I wasn't that kind of a guy. I was an artist or arty guy or whatever, not into science or mathematics or anything like that.
Skateboarding, you were pretty good.
Skateboarding, loved skateboarding, loved theater, got into music, anything but sort of stuff that required concentration and focus and applying oneself. And so out of high school, I barely knew that I graduated high school. Actually, I didn't know that I graduated high school at Tam High, where I went in Mill Valley, where I went to high school. Give it up, Tam High. Thank you. At the time, they didn't give out a diploma when you walked because that was the era of streaking. And they had this idea that, which actually the funniest part, worked, that the fear of not getting your diploma and graduating because you streaked would stop you from streaking. And basically it worked, but it's absurd, right? Like, fuck you. I did the work. Give me my diploma. I don't care what I wore or didn't through the ceremony. But at any rate, so the form was you walked, and then like the next day or the following Monday or something, maybe it was on Friday, and the following Monday you went and get your diploma. Well, I never went back because I didn't know I thought most likely it wouldn't be there. I had to get a C- or better in John Leidy's environmental chemistry class, and I didn't think I'd done that. So, didn't know when I graduated high school, played rock and roll around the Bay Area, not successfully, and I was bored working at a health food store in Mill Valley, and I noticed that when I would drive to go do a show at night, the stars were in one place, and when I would drive home, they'd be in a different place. It's like, what's up with those stars? Why are they moving? I had clearly not paid attention in high school enough so that the whole spinning on its axis that the Earth does, totally missed it. And even more intriguing, I did not have the logic to notice, wait, the sun does the same thing. So I went down to the local community college, College of Marin, to take an astronomy course to teach me why the stars were moving. And it had a prerequisite of a conceptual physics course. And I was like, physics? No way. But then conceptual physics, it was physics without math, so maybe it wouldn't, maybe it would just be a flesh wound. Maybe I could heal from it. And so I gave it a shot. And it was a perfect storm of lots of things. My psyche, my boredom, my willingness to want to change the pattern of my life, and this recognition. It was a beautiful, sweetly naive recognition at the time, but it's an important one, that there were these rules, these laws that govern the universe, and that you could learn them. And you could figure stuff out. Like there was a truth, an objective truth. It wasn't all just fuzzy and weird, and you could figure it out. Now, I've come to realize that some of those laws are just very good models that model a lot of what we see in the universe, but don't necessarily aren't written in stone, and that we modify them and add to them as time goes on. But when you're a young student, they can be, gospel. It doesn't matter whether they're perfect or not. And so I just dug into that. And at first it was really, really difficult because I had not learned how to study at all. I got mediocre or bad grades, and I was working really hard and not seeing anything pay off, and I was on the bubble for maybe a semester or two. And I can remember, I should have brought it with me. I should always have it with me. Somewhere in there, I was going to take a calculus course. So I had to start with elementary algebra, trigonometry, advanced algebra, and so on. I mean, I started really back where my 11-year-old daughter, is doing stuff that I was learning to do when I was 22 years old. But when I got to this place where I was about to take a calculus class, you needed a scientific calculator.
Most people hit the wall at calculus, I noticed.
Yeah,
I did.
It was it was a sort of a snowball starting to roll downhill. And I asked myself, the HP 15C, it's a little thing, right? Reverse Polish notation, really awesome calculator. And I said, Adam, you have dabbled in so many different things over the span of your brief 22 years. Are you going to really stick with this? Because it was $83. Now, $83 when you're working in a health food store, playing music at night, and riding your mountain bike over the hill to College of Marin is a lot of money. I said, I'm going to stick with it. So anyway, cool. I did. I still have that 15C. I don't use it. I use my iPhone. But I got good at it. And it ends up being that even though I'd convinced therapists and my parents and myself and every teacher that I was not a math guy or not in this thing, that was kind of bullshit. Which the great transformative, perhaps teachably transformative thing that I carry from that experience is that may go for everybody in this room, right? You may be able to do stuff that you don't have any clue about doing if you can get past yourself and find it. So it worked out.
Well, it's a great career for you as a motivational speaker.
Yeah, that's right. Tim Robbins, is that the name?
Yeah, there you go. But going from a bit of calculus and, okay, you got the physics, now you got it, why the stars move and stuff, to moving on into becoming a mechanical engineer.
Right.
What's that transition about?
Okay, so stars, physics, cool, love physics, crushing physics at school. I had gotten ready to be an arty kind of guy. The idea of getting paid and actually making a regular old Joe living day to day, getting up early and just going to work even though you don't want to, had been abhorrent. It had not been really part of my upbringing. And so I had to I decided in this part where I want to transform and change the thing that I'm doing, I decided to go for that. And engineering is physics that you get paid to do. It's slightly more practical, maybe a little bit more lowbrow, but someone's going to actually give you a decent wage and you'll be able to rent a house and buy food and that kind of stuff. So I decided, I had a buddy, Ray Grunig, who was a year ahead of me at the College of Marin, and he went off to go to engineering school. I'm like, that sounds pretty good, this engineering thing. They pay you and you get to go. And so I did it. And I loved it. It had all the physics, except it was also applied, so it was real, extra real. I loved the real of the universe laws that you could learn, and then I really loved the applying it, and actually it worked. It didn't break, it worked, and I'm riding on a bicycle that I designed and I welded up. Ooh, that's pretty cool. So yeah.
Okay, then you're starting to be an engineer. The idea of getting paid to do applied physics. did Caltech happen and then JPL? Or?
Yeah. So I did well in school, and I got kind of into doing well at school, kind of like, "Arr!" And I did really, really well. And so,
Is this because you were good at it, or you got some motivational heat going, or what?
oh, both, and they self-ate each other. So, I'd been like not applying myself for my entire life. So I had and also when we lived in England for a little bit when I was kids, and they thought, in the tiny little village where we were, they thought we were stupid, and then we came back and they did IQ tests on us to make sure that my brother and I weren't stupid, and so there's been like a lot of like, are they stupid? and so you go through a little bit of the are you stupid? Or are you just unmotivated? When I was in high school, I was in regular high school, and actually, interestingly, in sophomore year, as you can tell, I like to tell stories. In sophomore year, Paul Schwarzbart was a tiny little Napoleon of a man, French, I think, in extraction, and taught French and a couple of other Romance languages and Latin. And for some weird reason, I was taking Latin. And I was late for his class. And I knew that he just pounded on you if you walked in late to his class. So I sat at the edge of the door of his class, and I didn't want to go in. I waited, and time went on, and I waited a little longer, and time went on. And all of a sudden, the bell rang for the next class. So I went to the next class, and I was just sick to my stomach. I thought any moment the door was going to burst open, the principal was going to come in, or police officers, it was going to be terrible. But nothing happened. I went through the whole day, and nothing happened. So I went back to the next day, gets to time of Latin, and I don't go. Nothing happened. I tried it on another class. And another one. And pretty soon I'm going to the theater class and nothing else. My sophomore year, I have 1 A and 5 Fs. So the whole question, is he stupid? Is he unmotivated? They put me in a special thing where you can take more classes. They tried out he's unmotivated. So he needs to be more stimulated, give him more stuff to do. So then I got like 1 A and 7 Fs. So the point being that I'd had a lot of experience with the whole question of, are you a dumbass or are you unmotivated? And so when I started to taste motivation and started to feel not so dumb, those both sort of turbocharge each other. And I became very into that, into being smart and excellent.
Interesting. I like that sort of double discovery, the don't show up discovery, which I did when I didn't show up for Army Reserve after 2 years active duty.
That's good.
And the Army says you're supposed to show up. There's 6 more years of stuff, and fuck this. And I didn't show up. Yeah. And back in those days, they didn't come and hunt for you.
Really?
So it was great. I was liberated.
Definitely
I owe my life to that. And, clearly the age you got in theater took, if I may say so.
Right, yeah. That's true.
And stood you in probably good stead for being on camera in various respects and so on.
Yeah.
So this is a tough act to follow that you just showed us.
Yeah.
Is there another act?
So, right, I have garnered a lot of attention. That happens for many reasons that I can sit here and...
It has to do with hair and boots and...
Well, those things might help, but I actually believe that there's some capacity to communicate that's also a part of it.
I'm joking.
But what that sometimes, no matter how hard I try, that overshadows is that it's a tremendously large team effort. And actually, the greatest, most gratifying piece of this, there's a Teddy Roosevelt quote. There's many great Teddy Roosevelt quotes. One of them is that one of the great prizes that life has to offer is a chance to work hard at work worth doing. That's a good thing. One, that's work worth doing in my book. I have made a riff on that Teddy quote, which goes something like this: one of the great prizes that life has to offer is that great works require many people coming together to accomplish them. And it is that community, that teamwork, that interaction with others that is also uniquely human in how we do this uniquely human thing that we do. So, for me, the most gratifying part of this was working with an incredible team of people, right, that have just ideas coming out of their pores all the time, and sharp instincts and accurate analysis. I gathered that team of people together a few minutes before that happened. I'd done it first about 3 months earlier. And you know, in any big working environment, there's friction. It's not healthy also, but there's frictions and animosities and so forth. I gathered the team 3 months before landing, and I said, look, here's the deal. Our universe ends on the 5th of August. We're going to enter a black hole, and we're going to be spit out into an alternate universe. And whether it's success or failure, that universe is not an extrapolation of the one that you're sitting in right now.
Nice way to put it.
So, I want you to look around the room, and I want you to drink this in, because this is going to be over on the 5th of August. I gathered them again 3 hours before landing. And I said, because we were all sort of pregnant with a lot, you know, I'll do my best for selfish reasons and for generous reasons in my life to make something like this or even more happen. But if it doesn't, this will have been enough.
There's a line at the end of the 7 Minutes of Terror, Dare Mighty Things. Is that your line? Where's that come
Teddy.
from?
That's Teddy. That's the
Theodore Roosevelt said that? That's interesting.
Oh yeah, it was, yeah, absolutely. It's the, I'm going to try and bring it, give me a second here.
It was probably the Panama Canal or something that he
No.
was pushing.
No. It's a segment of, basically valor goes to the one with the dust in his face, who's broken. It's the fighter in the ring, right?
That's right.
Respect and valor go to the fighter in the ring, the one who's, is tried and failed, who knows both perhaps success and defeat, but does not know the shallow life of those who sit on the edge of the ring and spectate, that know neither success or failure. And so it is far better to dare mighty things and to fail than to never try. And that's where that comes from. I wish I could take credit for suggesting that. That video is an interesting study in randomness of the universe. The videographer who shot all of the headshots, actually who produced the whole thing, is a guy named John Beck. He no longer works at the Jet Propulsion Laboratory. John is a friend, and we had produced videos. He had produced videos over several missions, mostly for the people in the mission, right? There was the 6 Minutes of Terror for MER, and then there was another 7 Minutes of Terror for something called Phoenix, and then a mission called Phoenix, and then for this, we said, okay, let's make a 7 Minutes of Terror. And he couldn't get his people to give him the funding to do it. And he said, I'd like to put this one out publicly, and they weren't interested. So he said to me, hey, Adam, can we do this over lunch? Can you come to the studio and let's try and rough out some stuff? He had very different ideas, as with any good piece of art. It was going to go in a totally different direction than it actually went in. His image was Inception, the movie Inception, the trailer for Inception. He showed me the trailer for Inception several times. It was sort of Sam Spady. He has a light there, we're sort of thinking film noir. And we're doing it in front of a green screen, and he thinks he's going to find some sort of dark, static background, and so we go through this thing, and we do the whole thing, and he gives it to his people, and they're like, okay, you're in. They want it to be all me, and because of the thing, it's a team and not singles, we eventually pushed in the rest of the team, or small fraction of the rest of the team. But with the graphics and how he ends up putting it all together, it's a completely different thing. Everybody's like, that's pretty cool, and they're still on the bubble about whether they're going to release it. Oh yeah, okay, we'll release it to YouTube, and then kaboom, it's a big deal, and the viewership awareness of Curiosity's landing far outstrips any of our others, and it may well be. I think it's two things. I mean, really, social media is probably the biggest. The internet and social media, because I was involved in the landing of Spirit and Opportunity. And at that time, there were basically 4 or 5 television stations. There were more on cable, but really, the world paid attention to 4 of them. And they had nightly news, and the nightly news is going to tell you 5 things. And if you're the 6th on that list, you didn't happen. And so we were in the top of those lists, or in the 5 for like the first 3 days, woo! And then Britney Spears got out of a limousine, not wearing something, and all of a sudden we were number 6, and we fell off the radar. So here, this time, distributed information processing. So you think it's funny or interesting or cool, you tell him, who tells her, who tells those 3, and it all can happen without these sort of choke points of the conduits. So I think that's a big deal, and maybe this thing helped. The 7 Minutes of Terror may have helped that, chum the water before the event.
I'd say no question. You ended your talk kind of promptly, saying that space exploration, all of this outward stuff, is impractical but tells us something about ourselves and is telling us something about the questions we care about. And you're also suggesting that the skills that we're thinking about going outward go backward. Now, I have a history with this mirror effect, which is back when I said, if we're looking to go to the moon, we have all these photographs of the moon and all this stuff going out, and nothing's turning back and taking a photograph of Earth. And I said, hey, come on, do it 10 years after Sputnik went up, and 12 years after it went up.
I used that image, by the way.
Yeah, there you go.
Right.
And there were photographs of Earth, and indeed, it did change our perception of ourselves. So that mirror is real. I've seen it. What do you think is in a sense, the future of that mirror, of the reflection we're getting on ourselves from the space exploration?
Wow. I don't really know how to answer that. I think...
While you're thinking, you started to say that it's a cop-out to think of space colonies or somehow colonizing and terraforming Mars would be some sort of solution to Earth problems. Because if we could do that, we could, the Earth problems wouldn't need to be solved because we would solve them here.
Right.
With those skills.
That's right.
So that's part of it, but there's more.
Absolutely. Well, there's a set, right, so to that point, there's a set of risks, threats to humanity, right? Internal and external. We're doing a pretty good job, I think, now. I mean, there's some external that may just come in and just wipe us out, right? And you could argue that we should distribute ourselves across the stars to make sure that doesn't happen. I think the odds of that happening are relatively small, the external thing coming in and getting us.
Here.
And
unless, as we're learning how to, one of our previous speakers Lou said, we can identify the threatening asteroids, not the comets, but the asteroids, and deflect them.
Right. And so, the risks are relatively low. I think that the risks are highest from ourselves internally. And so, really, my push is to not think that, well, by the way, in terraforming Mars, I mean, that's involved, right? You have to have an understanding of how to balance. You have to have an understanding. You have to push an ecosystem in an entirely huge direction and have it find another equilibrium point.
Right.
That may exist or may not. I don't know. But that feat is tremendous. And if we can do that, then what are we doing here that we can't get in control? And there's a piece of it also about the appetite. I'm a man of very many appetites and big appetites, so this is hypocrisy. Never stops me. But eventually, I hope that the reason that we don't think we need to go outside is because we must keep growing. Right? There must be more people or more.
That argument's kind of gone away as near as I can tell.
Hope, because that's not a great argument.
Right.
And so it's something that we're doing wrong, and if the places that we would be going to, a world ship, that we design the ecosystem and set it up in perfect harmony and it doesn't go wrong, well, we co-evolved with an ecosystem right here that's in pretty good, even though we beat the crap out of it, it does pretty good for us. So I don't think our solutions are out there. That was the main push that I was trying to make. That mirror, for me, just underscores how precious and unique in the space that we can touch in millennia this place is.
The photograph of Earth from space that got people, there's sort of two. One is when the sun is behind the camera and you can see a full disk,
Right.
and that's what people imagine is the whole Earth. It just happens to be a version of Earth that's not a crescent.
Right.
But the one that really got people was the so-called Earthrise, which
Yeah,
is a
that
lie
one is
because the Earth
incredible.
never rises over the moon.
Right.
It's stationary in the sky. But here
Right.
was the satellites going around, and over the limb of the moon comes the Earth. They take a photograph and the video, and what people see is a great big dead foreground,
Yes.
Nevada on a bad day,
Yep.
and this tiny little, quite undeniably beautiful, blue, complicated, marble, living, fragile-looking thing. That contrast seems to have been what got people. And by the way, it's part of what people are getting from the movie Gravity, which says right at the beginning, in space, life is impossible. Basically, is one of the sort of captions that comes across the beginning. And then you spend the rest of the movie discovering how extremely impossible life is in space if you're
Right.
not inside all this incredible cocooning.
Right, absolutely.
So part of the bounce then is, in a sense, seeing life in contrast to death.
Well, when I'm working now, I'm leading the effort to develop a system that will extract core samples of rocks from Mars down past that 5-centimeter depth, seal them specially, individually, in a cache that could conceivably be returned by another vehicle at a later time.
Wow.
We're going to spend a lot of time and effort doing that. We're sort of scratching at, is there life on Mars? It looks pretty dead. If there's life, it's bacterial, it's pond scummy. By Earth standards, it doesn't look very alive, right? You go out to the center of Mojave Desert where there's nobody, and it's teeming with life compared to what we look at Mars. So that's the thing that I'm struck by is, holy crap, we're swimming in this warm pool of loving life. And that is very, very rare. When we go out looking for it in the rest of our solar system, and certainly even when we go out looking, we are finding thousands of planets around other stars. Or we will find thousands. We may be up to thousands already. It happens so quickly I can't keep track. But of those, there are a few that are, we aren't finding, and it's not on the numbers, in the Drake equation, I think there's a lot of them, but they are still very rare. And so that's my experience of that mirror. As I go out, as I design, as I help and people design spacecraft to go to these places, that we build them to live within these harsh environments, it doesn't feel friendly. And it does not look like this place. So that's my big experience of what I think is out there. Now, because all we understand are the laws that do a good job explaining the world around us, the universe around us, in this vicinity of us, there may well be dimensions or ways of travel that blow out my conception of the universe. And so going major places in a human lifespan, I think that's actually very
Major
interesting.
places, other stars.
Yes, let's talk about that for a very brief time. So we work on developing space projects to go explore space. There are some very interesting time constants associated with that process. There are things like 4 years, or 8 years, or 20 years. What's 20 years? 20 years is like the active career lifetime of a human being. So a person who is an advocate to do a thing is there and holding sway on that for of order 20 years. If you have a mission that is a 40-year mission, the person who starts it is not going to be the person who finishes it. And its continuity across that vision of what it is difficult. So when our expeditions go out many human time constants, it gets very hard for, it requires a very different set and very long thinking in a way that is unusual in us because it's way outside the time cycle of our lives. So anyway, that's interesting to me. And I think it's a slight challenge that projects that are many human lifetime constants in length face.
Well, I think we can thank the space program and you for helping us think in those many generations. And by the way, showing us that there is life on Earth. Thank you.
Thank you, sir.